Okay, hello everyone. Uh, have we discussed when we will have the midterm? This week or next week, right? Next week, the Friday, right? Okay, so I think I will continue for this part. At least maybe this week we can finish the diagonalizations, eigenvalues. I will just add like a small subtopics, which is actually related to your first engineering of math content, which is the differential equations. There are some methods. Actually, it is supposed to be, we have two methods that we are going to discuss again in this chapter, which is the undetermined coefficient and the variation of parameters. But I think I will just skip the variation of parameters because I think I need more time for that one. So I will just give you later the undetermined coefficient. So let me just get started from what we have from the previous discussion. So basically, when we diagonalize the matrix, we have some criteria. So based on the criteria, we can see the criteria based on the size of the matrix. Okay, we can see the size, and then how it will be having the independent eigenvectors, okay, or linearly independent eigenvectors. And if we have distinct eigenvalues, which means it's not repeated, then it will be diagonalizable. Okay, so we can diagonalize the matrix. Okay, if we have the distinct eigenvalues. So basically, what we are going to do in diagonalizations is basically we are going to find the matrix P, and then we are going to check whether it will sufficient with the structure of the diagonalization. So let me write here that basically we would like to find, just to give you some reminder, we would like to find the matrix P, which if we take the inverse of this P, multiply with A, multiply with P, this will be get into the D. This matrix D actually composed of the eigenvalues. Okay, and how we get the P? We get P from the eigenvectors. So we arrange the eigenvectors to be our P. We take the inverse, and if we put the inverse of P, multiply with A, multiply with P, we get D. Okay. But this structure is to confirm that this is true that P is our eigenvector, and then we get the result as P. Okay. So perhaps the questions that will be asked within this context of diagonalization is we could find whether the matrix can be diagonalizable, or can we find the matrix P so that this is true. Okay, this statement is true. So let's start with one example. Okay, just getting you the example. So to find these diagonalizations, the first thing is, as usual, we are going to find the eigenvalues. So first is find the eigenvalues. And then the second, eigenvectors. So first is taking the determinant of this matrix A minus lambda identity as usual. And then this will be lambda squared minus 10 plus 5, so it's minus 5. And then we have minus 50, and then plus 54, so plus 4, right? Okay. And then immediately we can factorize this. This would be equal to 0. -1, -4, right? So we have lambda 1 is 1, lambda 2 is 4. And I'm suggesting, just to make sure that we arrange really neat and clear matrix, what I'm suggesting is we can take the lowest value as lambda 1, and then we can increase the value number 2, number 3, just to make sure that it is clear. But actually, you can set in random value as well. Okay. The result should be the same. Although maybe the arrangement a little bit different, but the conclusion will be the same. So that's my suggestion, to help you to write in more clear and clean. So from this eigenvalue, then we could check each one of them. Check the eigenvector. So 4 lambda 1 equal 1. And since this is distinct lambda, so we say that this is going to be diagonalizable. Okay, so we now find the matrix P, which is composed of the eigenvectors. So we can find, first is -5, -1, so -6, 9, -6, and then this will be 9. And then we take the row operations equal to 0, and then solve these equations. Okay. I will just write the final results. Okay. We are going to get the K1, 3, 2. Okay. And then check the lambda 2 equal 4. This will be, I'll just write the final answer here. Okay. But basically you need to solve this and see the which one is going to have the infinite solutions, and we can let that as a number and then input the other value as well. Now using these vectors as P from the eigenvectors, then the third part is arrange matrix P. So P will be column of the eigenvectors 1 and eigenvectors 2. Notice that whenever you make changes, the arrangement may be different. Maybe you say this is 1, this is 2. You will see that this will also going to exchange. And basically when we multiply, we get the same conclusions, that they are going to be diagonalizable. So we get P using these eigenvectors is 3, 2, 1, 1. And then take the inverse. The determinant will be 3 minus 2 is 1. And then we are going to just take the take 1 here, take 3 here, 2 will be the same, but we are going to multiply this with negative, right, for the 2 by 2 matrix, for the inverse, right? So we get this as our inverse. And then we need to prove at the end, to prove that this is true, that so check the P inverse AP equal D. Okay. So we check through this multiplications. and then A, what is A? Is negative 5, 9, 10, and then P is 3, 1, 2, 1. So we could check one by one. So maybe first going from the left if you want, or the right also will be the same. So I think I will just give you the final result. This should be true, that this will be equal to 1, 4, 0, 0, which is our D. Okay. And this is true because this 1 is the lambda 1 and 4 is lambda 2. So this is true. Now if we take maybe the K1 and K2 we flip and we change the 1 and 2 be maybe 4, 1 instead of 1, 4. This will be 4, 1 at the end. So should be similar conclusions. So it means that actually you could do like 1, 2, 3, 4 with whatever order you have. At the end, it will be the same conclusions. Maybe just different arrangements. But my suggestion, to make it clear from the very first computation so that you can make through in your paper, you can start taking the lower values and increase. Just my suggestion. And whenever we find the repeated eigenvalues, then it could be not diagonalizable, but it could be diagonalizable. I can maybe later I will show you what it is. Okay, so this will be diagonalizations. Okay. Maybe let me give you notes here on the right side. Sometimes, if we have like 2 by 2 matrix, for example, if we have a repeated, so suppose that we have A, 3, 1, negative 1, 4, 7. If we check the eigenvalues from here, we get that this will be 3 minus lambda, negative 1, 4, and then 7 minus lambda. Now if we multiply, this will be lambda squared, negative 10 lambda, 21 minus 4, 21, oh, minus 4, so 25. So this will be a repeated value. But since there are only 2 eigenvalues, which is lambda 1 and lambda 2, we say that this is a true distinct, right? True distinct. Like every eigenvalue will be, it's different, right? So we say that because this is repeated value, or or lambda, then it is not diagonalizable. Okay. But there are other conditions where if we have the 3 by 3, for example, if we have 3 by 3 matrix, we can have maybe 1 and 2 are repeated, but the other one is distinct. They can have diagonalization. They can. But we need to confirm. Okay, that's the problem where we need to confirm. Okay. Let's say another example. Let me just squeeze this into small sections just to show you that we can have like a not non-diagonalizable matrix. So let's say maybe take different variable b. Let's say we have 0, 1, 0, 1, 0, 0, and 0, 0, 1. Now, if we check the eigenvalues through its determinant, which we can find, I think, either row 1, row 2, or row 3, you can check later, but this will give you lambda 1 is -1, lambda 2 equal lambda 3 equal 1. And if this happens, then we need to take this into our confirmations through the finding the p. Okay, finding the p, finding the eigenvectors, and then we find the p, and then we multiply, and we check whether the final results give the eigenvalues as a result. Okay. So from here we get the k1 from the row operations through the lambda 1 equal -1. This gives you 1, -1, 0. K2 is giving you 1, 1, 0. And K3 is giving you 0, 0, 1. After some parameter choices, we can choose, usually we choose one variable to be 1 or 0 to make it easier to compute. And then we can choose perhaps p is based on this. And then check the p inverse AP equal D. And if we check, this will be going to be true. Okay, this will be going to be true. And one thing for the repeated eigenvalue in this case, if we check through the row operations, we are going to have like a 2 slots of the rows. They are going to have like an infinite solution. So it could be many choices and possibility, which we need to take the some value, and then we can have 2 eigenvectors. And of course, at the end, like how we get this K2 and K3 is we need to make sure that all of these eigenvectors, they are linearly independent. Okay, that's the diagonalizations. Okay, basically, we are going to carry this structure into differential equations. Okay, and hopefully, I can give you some, at least an introductions to how to solve differential equations through this diagonalization. Okay, now let's move to the next page. when we have the time, I will review on some practices. So suppose that we have this. This is, we call the coupled system. For the homogeneous linear system. This is x prime a x, okay? And of course this x prime in all the in this column, this will be linear combinations of the x1, x2, and xn. So this could be understood as xi prime is expressed as linear combinations, as we have seen from our differential equation standards of x1, x2 until xn is we call coupled okay. And then the second statement is if A is diagonalizable, then system can be uncoupled so that the each differentials, the x prime, can be expressed in terms of the x. And so, based on this, I think I write too big. Let me make it smaller. And let me zoom in and make it smaller. Okay. Okay, if A has n linear independent eigenvectors, then we can find basically the same as previously mentioned, the P, so that the P inverse multiplied with A multiplied with P is equal to D, where D is, this is diagonal matrix. Okay, now from this part, then we make substitutions. That is, let me write with green. X equal Py in the system of the original differential equations, which is the x prime equal ax. Okay, so we are going to change, to substitute the x equal P1. So P1 we're going to substitute to there, to our system. So x prime is going to be py prime. So we can write, maybe let me write here. So x, and we x prime equal ax. This will be py prime a py. Okay. And then I will multiply the left with p inverse, so that I can cancel p inverse with p. So we get dy inverse equal p inverse a p y, right? And this part here is our diagonal. So we can write the final result as y prime equal dy. Okay. Now this, if we break down the matrix, this will be y1 prime, y2 prime, dot dot dot, yn prime equal. Now if you remember, the d is actually our eigenvalues, which is in the diagonal matrix. So lambda 1, lambda 2, dot dot dot. This is lambda n, and then this will be y1, y2 until yn. So the solutions, or if we see the differential equation first, we can make so since this is our diagonal, so this is d, right? Each differential equations, let me write here, is in the form of yi prime, let me write with green color, yi prime equal lambda I yi, where I will be from 1, 2 until n, which gives you some idea on the solution for this system. Remember, in the homogeneous system, our solutions are atypical of the exponent, right? The exponent with power of t, eigenvalue t something, right? So we could write the same solutions when we get this eigenvalue. So we could offer a solution that is going to be y equal a constant multiplied with the exponent. So our solutions become will be yi. Let me write with the red color. So yi equal ci e with power of lambda I t. And of course, I started from 1, 2 until n. Let me resize this first to make it space. Okay, and then we could write a general solution. We can write y equal c1 e lambda 1 t t, c to e lambda 2t until c and e lambda n t. Okay. So we get now our general solutions. So we can obtain the solutions for the system x prime equal ax from this substitution x equal py. Okay. So this is what we call as a uncoupled or uncoupling. So the coupled is actually the x prime and x. So basically we say that when we substitute this, it basically separates this x prime with x, and we have now the y expression. But the idea is still the same. We start from the eigenvalue and eigenvectors. We arrange the P, the matrix P. And then the solutions will be based on the x equal py. And don't forget here, let me give you some notes here. That after we get y, it's not the final result yet, because our final result should be going to be x equal py. If we still have this x as our main problem, which we need to multiply. So we need to multiply all this column y with p, so that we have this x as our solutions. Okay, let me give you an example. Okay, how this works. Okay, how this works. So basically, finding eigenvalues, finding eigenvectors, finding matrix P. Okay, so that we can diagonalize, and then we need to arrange our y. We arrange our y, and then we need to multiply back with the P. The P is equal to y. This will be our final solution. So let me give you some example here. So we have this x prime, we have the matrix, so we have the A, so let's say this is A. And then the first thing we need to do is finding the determinant. Oh, okay. So we can check the multiplications for each one of them. But let me just give you the final result for the eigenvalue. So suppose that we get that this will be equal to minus, I will give you the final factorizations, which gives you all three eigenvalues, and all of them, they are all distinct eigenvalues. So since they are distinct, we could also say that they will be linearly independent. And then solving for each eigenvalue, solve for each lambda, that the A minus lambda I multiplied with k equal to 0. So you might use some row operations here. And let me give you the titles here. This is eigenvalues. And then the second part will be getting the eigenvectors. Now from here, for each one of them, for each lambda 1, lambda 2, lambda 3, we're going to get, we get k1, this will be equal to 1, 0, 0. K2 will be 2, 2, 1. K3 will be 1, 1, 1. Now, of course, that since we have many repetitions on finding eigenvalues and eigenvectors, so I hope you can try. Just make sure that you are familiar with these eigenvalues and eigenvectors. Okay. If you have still finding it, maybe still have some something that is still not clear, please let me know. Okay. And then from this K1, K2, and K3, we get the matrix P. That is K1, K2, K3 as in each column, right? So we could write now the P is 1, 0, 0, 2, 2, 1, 1, 1, 1. And then our D, based on the criteria for diagonalizations, this will be directly -2. But of course, we need to confirm that this is true. This is based on the lambda 1, lambda 2, and lambda 3. Right? And from this lambda and our D, we could immediately get y prime is dy, which gives you y is actually going to be C1e -2t, C2e t, and C3 e with power of 5t. Okay. Now the solutions, since it is x is equal py, then our solutions will be x equal p is 1, 0, 0, 2, 2, 1, and 1, 1, 1. We need to multiply all of them with this, all of this y. Okay, and practically this is the solutions. Okay. This is the solutions. So this could be written as X, C1, and we can nicely write each column. The first one here with the first row in the Y. So this will be E with power of negative 2, 2t, and then plus 2, 2, 1. And this will be E with power of t, and then plus 1, 1, 1. Let me and then E with power of 5t. So let me write and make a claim here that this will be work so well. Diagonalization works really well when we can find n linearly independent eigenvectors. Of the n by n matrix, matrix A. And remember, the eigenvalues, it could be distinct, it could be repeated value, or it could be complex. And when you have repeated eigenvalue, you can have two choices. It could be linearly independent eigenvectors, or it is going to be dependent, which will be fail. And that is when the situation is going to be, it's not going to be diagonalizable. So we cannot use diagonalizations. So this is for the homogeneous, okay, for homogeneous. So for homogeneous, we have several ways. We could find through three cases, basically: the distinct eigenvalues, the repeated eigenvalue, and the complex eigenvalue, which they have each of case, they have their own characteristics, right? And then we have now the diagonalizations, which I think based on the computation that we can make, this will be, I think, not really that much. But of course, the first and second process will be the same for all eigenvalues problem. We need to find eigenvalues, we need to find the eigenvector. That is for sure. So every part of the matrix, this two will be the very first process. So you need to be able to familiarize with it. At least 3 by 3. And of course, I also think that because answering one problem may be taking like really longer time, right? So I will think through how to set up the question for your exam. Okay, so the last part from this is actually the non-homogeneous part, which I will tell you the one method that we have done before, but we are going to make it into the matrix system. I think that will be for this Friday classes. And also we have some, I think I will also provide some exercise, maybe like 5 to 10 questions, or maybe 5 to 7 questions that maybe represent all the system of differential equation in matrix. Okay. I will try to find the question first this week, maybe by the end of this week, or maybe Thursday I can give you, and maybe some part of them I will discuss this Friday. Okay. So I think that's all for today.